Hello, this is a project for Aerotech Fall 2020 Senior Design Project. My name is Brian Patrick Farron.
I'm Keegan Alloway.
I'm Cameron Casalis.
Tyler Eklund.
And we were tasked with designing and building an automated handling system for small camera lenses. Alright, so we're going to do a general overview of our project first. Everything sits on top of a stainless steel plate. Underneath we have our 80/20 frame. Along this side we have our electrical components, our pneumatic components, and then we have the robot itself, which is talking to the camera up here.
Quick notes about the frame and the plate setup. It's important to ensure that all the bolts are properly tightened down. The edges are square, and that'll help with the transform between the camera and the robot arm to put all the real world coordinates in order.
Alright, so a quick note about our vacuum assembly up here. It's composed of several parts. Down at the bottom here we have a part called the vacuum gripper. This interfaces with the lens. It has a small hole right there where the air flows. This component mounted on the robot is what we call the quick release system. It easily allows you to change these heads out if necessary. And then we just have our vacuum hosing. Two pieces actually, so we have a union connector right here, and this allows you to change out the vacuum hose if needed, if it's leaking or you want to have a different sized head in there, so just so it's all customizable. I'm going to put that back together real quick. Goes in like so, and then you just pop this right back in, then you're good.
Alright, so now we're going to go a little bit more in depth with each component, starting with the robotic arm. This robotic arm is a Troson Robotics RX150. It's powered just through the wall with a barrel jack over here. When you plug it in, there's little lights on each servo that turn red, so you can see that it's getting power. They only turn red for a quick second. Next, you plug it into the controller, which is a micro USB to USB just in your laptop port. So plug it into the laptop or whatever sort of CPU you're using, and there should be a red light here that shows it's connected to the controller. Next, we're going to talk about the camera. The camera is an Intel RealSense D435i. It's plugged in just through a USB-C to USB 3.0. Preferred 3.0, you can use 2.0 if you want, but 3.0 allows for faster and more data transmission. Important thing about this is make sure that it's level across the length of it, so that transforms aren't messed up when recognizing pixels. But yeah, plug in USB-C here, USB 3.0 here. Everything will be going well. The robot arm has this red tubing coming out of it, which leads over to our vacuum generator system, and we'll go in depth with that now.
So now we're going to go over the vacuum system. So the vacuum system works by a vacuum generator and suction. Comes by the head over here, pulls air out. This is the vacuum generator. It works on the premise of pushing a pressure through a nozzle. So this is the vacuum part, and then this is the pressure part. Pressure part comes from a air compressor. So the air compressor comes in, get plugged into this side. How and what this is a solenoid. So this works on, this is the electrical portion, vacuum portion, so the pressure comes in this side. The two on the side, these are both connected to the same thing. We have it cut off by just taking one of the pressure hoses, bending it over with a zip tie, it's cut off. So you have that. Then when the solenoid is turned on, you have pressure come out the top. The solenoid is controlled by a normally open contact. When electricity is supplied to this 120 VAC, closes the contact and air pressure is able to flow. This is controlled by a line neutral and ground, where it's just 120, so the line neutral or orange, and then the green is ground, goes into this Arduino assembly over here, where right here we have the line coming in to a 5 amp fuse. You're able to pick it up, change out the fuse if you need to, right here on the inside. Line comes out into a terminal block where it comes over to the Arduino, and the Arduino is a normally open contact. So then if we plug in the Arduino, we've got a USB, I believe it's B, comes into here. You take your other side, just regular USB A, plugs into the laptop or whatever you're using. And the idea is that the code will tell the Arduino when to open or close based off of the location of the head. So when this closes, it allows electricity to flow into the solenoid. Solenoid turns on, allows pressure to go into the vacuum generator. Vacuum generator pulls a suction in the robot.
Now that everything's set up and plugged in, we're going to move over to the workstation to actually get everything running. Okay, so now we're here in the main workspace, main directory of our workspace. Aerotech Robot Arm is the name of it. Inside, you can see there's a bunch of different files. The most important one is probably the SRC. That's where the main source code is for all of our nodes. We've broken it down into 3 sections: core, perception, and robot arm. Robot arm obviously has to do everything with the arm. Perception has to do everything with perception or computer vision using the camera and deep projections and things like that. And then core is just sort of miscellaneous, but everything that's core to the robot. So if we go inside of core, we'll see that there's a TF lookup, which helps us transform points in the camera frame to the robot frame. And then most importantly inside of core is the main launch file. So in core launch, there's the main.launch. So main.launch, and one note is most of our source code files have a comment at the top that kind of say what the file is, what's important about it, what role it plays in the whole autonomy stack. This is the main launch file, so it launches all the nodes necessary to run the robot autonomously. So it's just a regular ROS launch file. It has a bunch of arguments in the README, which I'll show a little bit later, or you may have already seen. It sort of explains what these arguments are. These default values are values we were using when we were testing on our setup, but feel free to change them as your parameters change. So what this does, it launches all the nodes necessary to run the robot. So it launches the robot, which is another ROS launch file found if you want to go look at it, robot arm launch, robot.launch, launches the camera, launches the TF broadcaster, which is the static transform between the robot base and the camera, launches that TF lookup that I was talking about a little bit earlier, which basically transforms points. The pixel deprojection launch, which is found in perception launch, deproject launch, is basically taking pixels found in a image and transforming them into 3D real world coordinate points. We have an argument here, use neural network, use NN. If we're using the neural network, then we launch the neural network. If we choose not to for some reason, then it launches the blob detector. Launches this pick and place node, which is basically the autonomy node that we wrote, which is robot asks for a point, gets a point, moves there, picks it up, moves it to the target, places it. So we call that pick and place. And also launches ROS serial, which is how we talk to the Arduino to tell it turn on the vacuum, but really just flip the relay switch. Okay, so now that that's done, to launch everything, we've created a Docker container, which is going to help out with sort of running this on systems that don't have all the dependencies installed. You don't want to go through the hassle. The Docker container has all the dependencies installed for you, so it's simply just build it and then you can run it within the same hour that you get the robot. So if we see here, it's all under deploy, right here, deploy. So if we look inside of deploy, you'll see that we have some Docker files and then some other shell scripts that help us launch everything. So if you look in the README, it will tell you how to deploy the Docker. So first you want to set up the UDEV rules, which basically open up the the USB ports on your machine so that the Docker can access them, and then deploy. And then when we're in the container, we'll run robot run. So let's first set up the UDEV rules. So I always do sudo just in case, deploy, and then set up host UDEV. Okay, so that's setting up. Done. So now deploy the Docker container, and this takes a little while because it has to build everything from source. So we'll probably speed this up, and I'll see you after it's done building. Okay, so now we're in the Docker container. You can see here that now instead of Airtech robot arm, you're in this Docker container workspace. If you list, it's still the same workspace, so it's copied all of our files into this Docker container, which is great. So if you go to source, you'll still see core, and if you go to core launch, you'll still see main. So everything's still the same. You're just in a container to make it easier for us to run on any machine as long as you have this Docker daemon. So let me clear the workspace. So now we're going to actually run the robot, and so that's in this nicely named file called robot run, which does some things. All you need to know really is that it just calls ROS launch core main.launch. Doesn't do anything really that special. So now that we're in the Docker container, you can run robot run. It will launch all the nodes that we talked about earlier in the main launch file, and it also opens this thing called RViz. RViz is ROS's visualization software package. So you can see the robot. It's in a weird position right now. But as I move it, it will move in RViz. So I'm just manually moving it. The motors are torqued right now, but you can still see it's moving in RViz, which is cool. Another thing that RViz is useful for is visualizing what the camera is currently seeing. So if you go to these topics, so what I did here is these are all the topics you can visualize. I click add a new display by topic. So each topic is named. So camera, color, images, raw, and then the image is what we want to see. This is currently what the camera's seeing. You can see my hand if I put it under there. So that's currently what the camera's seeing. So you can drag that over here, wherever you want it to be. I'll just put it here for now. And then I'll add another one. Then I'll add another one. I'll add the neural network detections. So we are using the neural network currently. And so right now, it sees there's no detections, right? Because there's no lenses in the view. The lenses are under this black piece of paper I have placed. Put that back there. So now we have neural network detections over here. So if I move this piece of paper, the neural network will detect the lenses. Every lens it detects, it puts a box around. The box is green for the lens it's going to go to and pick up, and it's black for all the other ones. And there's also another mode that we have for if it's out of range of the robot, we box it in red. So I'll move the camera lens, and you'll see it's updated, and now you can see the robot's moving, and you'll see it come into frame. It goes down. I have the vacuum system unplugged right now, just for testing, but you can see, so it would have picked it up, moved. So you can see everything, sort of the whole thing play out. So if we move one lens, the detection will get updated next time the robot is at its resting position, and there you can see it's updated, and the robot's moving to pick up that one now. So that's how you get the robot started and running. I'll cover up the lenses again so the robot stops moving in the background. And so as you can see, the robot will stay in that sort of home position until it finds a lens to go to. So I'll close RViz for now. I guess there's nothing really else that important to see. Usually when we're testing, we only look at the camera image, color image raw, and then the neural network detections. But feel free to play around with sort of anything. I guess one thing to talk about in here is that this is the camera. So this TF here is called the TF frames. These are all the frames. So everything with RX-150 is given by the robot manufacturer, so we have no control over that. So usually we can turn those off, and you can see them disappearing from the robot right now. So now there's nothing on the robot. And then the camera, they're all given by the camera manufacturer. So I turn off everything except Camera Link, just so it's less cluttered. So there's Camera Link. And that yellow line you see is the transform between the robot's base link, which is at its centroid down here, and the camera's camera link frame. And so that's what you're hard coding when we talk about transforms and everything. We're hard coding the coordinates of this yellow line. So if the camera moves, or if the robot moves, or you rearrange anything, you'll need to update that transform so that the robot knows where the camera is, so that it knows where these lenses are when they get detected. Yep. So if I close RViz now, you can just press discard, because that's not really that important. One thing to be careful is you don't want to just Control C to kill the robot while the robot's up, as it will fall as all the motors get untorqued. So you want to have one person holding the robot while the other person press Control C to kill the robot. And then you want to make sure the robot goes safely back to its resting spot. So we talked earlier about if you'd like to change the command or the default arguments in core main.launch. You could come in here and change just default values. That's certainly a way to do it. Another way to do it is in your command line when you're launching, so ROS launch core main.launch, or inside of robot, if I open up another terminal, if you go to robot run and you add to the end of this line and this line, wherever you're launching, just go in here, say you want to set neural network. So if you remember, neural network use NN is default set to true. Say you don't want to use the neural network. So you just say use NN colon equals, which is how you set arguments in ROS, colon equals false. You don't want to use the neural network. Launch everything. RViz will pop up again. Everything is exactly the same except you're not using the neural network. So if you go into these topics again and look for NN detections, you're not going to see it because we're not using the neural network. Another way to check what nodes are running when everything's running is to do ROS node list. Obviously, I just killed everything, so we're not going to be able to communicate with master. But say I didn't kill everything. You can go in here and while everything's running, ROS node list. Here are all the nodes that are running. So the neural network, the pixel to point, the Arduino bridge, all these different nodes are running. Robot move node, which is the pick and place. So all these things are running. If you want an even more granular look, you can look at the different topics that are running. So those are all the topics that are being published. And then if you want to look at the TF transforms between everything, this one sometimes takes a second. So this is the TF tree. So we have the world to the base link, which is the robot's frame, and then this is the static transform that we are broadcasting. So world and base link, those are controlled by the robot. Robot also controls all of these, so you don't have to worry about setting those. Those are set by the manufacturer. These are also set by the camera manufacturer. So the only thing that we are controlling is this arrow from base link to camera link. So that's what you can change in the ROS core main if you need to move the camera. So we can close that. Another thing that sometimes is helpful is if you do the RQT graph. That shows how all the nodes and messages are publishing to each other. So if I zoom in a little bit, you can see this is the camera. All of this is controlled by the camera. All we really know is that this camera is publishing to the neural network detector on the topic called camera color image raw. So camera color image raw gets published to this neural net detector, and that outputs a bounding box center to the pixel to point node, right? And so, and then this publishes, so back over to the point transformer. And so this is, if you follow these arrows, red means a node, green arrows are what that node is publishing, blue arrows is what that node is subscribing to. So if we look at the robot move node, what does the robot take in? So the robot takes in a detection with the real center in the base link frame. So where are these lenses in our coordinate frame? And it takes in the joint states, which is controlled by so everything in these boxes is controlled by the manufacturer, more or less. These joint states basically say what are the states of each joint in our robot. So that comes into here, and then it does some inverse kinematics to get to where it's at to where it needs to be, which is this real center base link. And then what does it output? So it outputs a command to the vacuum. We call it vacuum just for easy naming, which talks to the Arduino. The Arduino flips that solenoid on, turns on the vacuum. This also talks to the neural network detector. So when it gets to that home position, it asks the neural net detector, okay, run detections, get me another point. So we have a green arrow there because we're publishing to neural net detector telling it, okay, we need another point. Also, this arrow you can see here is publishing to the ARM node. So this is a joint trajectory. So this is talking to the ARM node, giving it its planned trajectory, and then it returns back where it's actually at. So basically it can do some PID control or whatever the internal controller is using. I don't think there's anything else that's too important. The pixel to point does what it says. It takes in a pixel from the bounding box center and outputs a point, and then the point transformer transforms it from the camera frame to the robot frame and gives it to the robot. Nothing else. Camera to base broadcaster, that's our static broadcaster. So it publishes a broadcaster to the point transformer and to the pixel to point that transform between the camera and the robot. Arduino bridge, we talked about that. Neural net, we talked about that. Robot move, we talked about that. So like I said, everything in the rectangles is controlled by the manufacturer. Everything outside of the rectangles it was controlled by us. And so that's our total ROS network right there, if you will. If you want to, say you're testing and you want to publish a message, so say you want to turn on the vacuum, you would do ROS topic pub, the topic name, and then if you keep pressing tab, it will fill out mostly everything for you. And so say you want to turn it on. If we turn it on, you might be able to hear the solenoid click or the relay click, but you'll hear no air because it's unplugged right now. And then if I want to turn it off, you'll do the same thing, but turn off. And so that's one way that you can publish messages. You can also publish to different topics. So whatever topic you want, you can publish to. So say you want to publish to, you want to give the robot a random point to go to. You can put the points in here, fill it out 1, 2, 3, and the robot will try to get there. So there's different ways to publish things when you're testing and debugging, which is something we used a lot when we were working with this. I don't know if there's anything else that's too important. We talked about deploy. We talked about source. So in the source, we talked about where there's broken up into core perception and robot arm, the different launch files in there and the source files in there. Yeah, so good luck. There's the readmes very in depth, and there's lots of the code's very commented, so it shouldn't be that hard to get things up and running and debug when you need to, if you have a good understanding of ROS. And there's mostly Python nodes for the robot arm and the Arduino, but then we have C++. All the perception and camera stuff is running on is coded in C++, and everything else is Python, more or less. So if you have a good understanding of ROS, C++, Python, and you can read the comments, everything's pretty straightforward. So for example, if you want to see how the robot arm, we have that pick and place node. So we make this bigger, you'll see, like I said, all of our source files have a comment at the top saying what's going on, what is this file. So you have all your imports, we have our class. So you read through that. This is basically setting everything up, the init, and then most of our functions have a nice doc string too, talking about what's going on there. And then there's comments throughout that are helpful as well. So well documented. Also the readme's there if you need help, and yeah, it's not too bad. Well, thanks for sticking to the end. I wish you the best. Good luck.